So I'm not Todd, but I do work with him. I'm a software architect on the Intel OMNI-PATH architecture team. Fairly new to Intel OMNI-PATH. I was previously on the Knights Landing, Knights Corner, the Xeon PHY line of Intel's products. What I want to talk about, actually, before I start, how many of, PSM was mentioned at least 4 times in the last 3 days. How many of you have heard of PSM? How many have you actually seen PSM use PSM, the APIs? Mostly my Intel guys, okay. So this is good. I want to talk about PSM. I want to talk about what PSM is, talk about sort of its history and new features in PSM2, and then talk a little bit about compatibility with PSM1, the previous generation of PSM. I'll do a shallow dive. I won't do a deep dive. I don't have enough time to do sort of PSM architecture. You'll get a sense of what PSM does underneath the covers. And then I'll talk a little bit about PSM and OFI. Sean talked about this quite a bit. And then briefly touch upon what PSM is as far as open source. You can go see the code, it's out there, and so on. Before I go there, I'd like to give you sort of a big picture perspective of where PSM is. So what I'm showing on this picture here is sort of the big host software stack, right? On the far left is the black boxes, which is the existing OFA verbs stuff and ULPs, IP or IB, SRP, ISER, that type of things. That still exists on Intel OPA. We haven't touched that. We support that, obviously. There have been a number of talks. Ira talked about it. There have been other talks as well. So you can use existing verbs application and existing ULPs just fine. On the right is the OFI providers, including PSM, and I'll talk about that, and new middleware components like OpenMPI and MPitch and so on that support OFI. And in the middle is PSM, and you can see that PSM is sort of a parallel stack to verbs. It's not verbs, it's a different parallel stack. And what I'm going to focus is on that red circle. But our strategy is basically leverage everything the OpenFabrics Alliance is doing. We don't want to abandon that and so on for the reasons I mentioned. But we also wanted to sort of take our robust PSM software stack that we've had on TrueScale, Intel TrueScale, and move it forward to Intel OMNI-PATH architecture. And in that process, we call it the 4th generation now. In that process, we've sort of made enhancements to it, which is the topic of this talk. As far as access goes, all of this is open source. We work with it's in GitHub, it's in the Linux kernel. We work with distros like RHEL and SUSE to get all this in. So it's out there. In addition to the host software stack, the fast fabric tools, the fabric manager, the fabric manager GUI are all open source as well. So you can go see them. So what is PSM? PSM is a scalable messaging library for large clusters supporting millions of ranks. Basically, we looked at verbs, and we said we wanted something that was more efficient and semantically matched to the needs of MPI. So if you go actually look at the PSM API, you'll actually see things like, you'll see parallels to the MPI API and the PSM API, and you'll see why it's that way. But it was carefully designed to basically do things like efficient tag matching, efficient match queue semantics and stuff like that. There is it's based on an endpoint communication model. So basically, you have endpoints that talk to each other, and fundamentally, it's an object that you instantiate in PSM. There's a PSM Open and there's a PSM Connect API. And an endpoint basically lets you manage flow and do reliability between endpoints. So things like packet sequence numbers. There is a key component of PSM called match queue, provides tag matching. It also provides the sort of standard match queue FIFO semantics, which is things like, if you look at the MPI API, there's MPI send, the standard send, and then there's MPI send or synchronous send, where before MPI sends a message across, it makes sure the receiver has posted a buffer that this buffer can land on, that type of thing. And the PSM MQ API actually has options that you can pass in to do these kinds of things. Finally, it's all about performance. So PSM is optimized for both latency and bandwidth. So we sort of handle the case where you're sending small messages with MPI as well as these big bulky transfers. And I'll describe how we take advantage of both the on-load architecture of Intel OMNI-PATH as well as the offload architecture of Intel OMNI-PATH to support both those cases. And then finally, like everything else, it's the PSM API hides the fact that you might be both on the same node or you might be talking across the fabric, but it sort of efficiently handles both cases. And then there's a pretty robust error handling scheme. If you look at the PSM documentation, I have a link in this slide deck on that. There is, you can define per endpoint error handlers, you can define global error handlers, and you can say, I want to defer everything to PSM and let it be. Right. So the PSM API, the sort of previous generation API, was pretty good. It had 64-bit tags, so you can do things like, a tag can consist of a sort of communicator, a source rank, and a tag, right? The source rank itself was 16 bits, which means you could do about 64K ranks per job. And the message passing API, things like PSM2 send and PSM2 receive and so on were pretty standard. There was no receive from functionality, which means that MPI at its layer had to make sure that if it was receiving a message from a sender, it had to sort of look at the message and say, oh, I know where this came from, and do things at its layer. So in PSM2, we basically took that, we sort of looked at PSM, we looked at MPI even closer and said, let's improve on this, right? So we made the tags, we increased the tag size from 64 bits to 96 bits. This allows us to define a source rank for up to 32 bits. We actually only define 26 bits. But fundamentally we also have a tag selector. And so now you can actually say, I want to receive messages from this tag. And it's basically that operation. It's an exclusive OR with a set of mask bits on it. And so this allows you to do things like, you can say, I want to receive messages from any source. I want to receive messages from any tag, the stuff that you're used to if you're writing MPI applications. And like I mentioned, the bits that constitute the source rank now are 32 bits long. So you can define practically unlimited scalability as far as the job size goes. And then lastly, a lot of the new PSM APIs in PSM2 allow you to specify the source rank from which you can receive a message. So you can say, I want to receive a message with this tag only from this source. And PSM will take care of that. And this is the last point is the most important, which is the Intel OMNI-PATH architecture is optimized, heavily optimized to run on PSM2. So we sort of designed PSM2, we said, how do we optimize Intel OPA to make PSM2 scream, essentially? So there are several performance and scalability improvements, both in OPA as well as in the software layer, which is a whole talk in itself, so I won't go into that too much. Now, quickly through the APIs, this is what the new 96-bit tag looks like, and you can see there's it's essentially a union of an array and 3 bits. But basically, an application fills up this tag and defines a mask, and the mask is essentially the same structure. And you just say, I care about these bits, I don't care about these other bits, and so on, and you use it in your APIs. So, for example, and by the way, the way to tell if it's a PSM1 or a PSM2 API, but sort of previous generation versus the new generation is that 2 at the very end. You see, I send 2. That's the new stuff. So the thing highlighted in red would be a 64-bit value in the previous API. Now it's a 96-bit tag. And so this is an example of a non-blocking send or a blocking send that uses the 96-bit tag. On the receive side, you normally post receive buffers. If you're doing some kind of an asynchronous receive, for example, you can get a status back when you sort of retrieve the message. And what we decided was in the status, we extended it to do 2 things. One was to sort of provide like I mentioned, the source of the buffer, so the peer from where the message came from. And it also lets you provide the 96-bit tag that I mentioned earlier. So you can actually define larger tag values. So this is what the receive side functions. And by the way, this list of APIs is by no means the exhaustive list of APIs that PSM supports. There's a huge list. The documentation covers all of that. I just happen to pick a few for this talk because they seem kind of cool. But things like probe, if you've ever used MPI probe, where imagine you're an application writer and you say, I have no idea what kind of a message I'm going to get. I don't know what data type, integer, float, I don't know. So what I'm going to do is I'm going to probe for messages, and when I get a matched message, that will tell me what type of data has arrived, and then I'll do a receive to receive that kind of data. I don't know how long it's going to be. I'll know after I do a probe, I'll know. So that's kind of what probe does. mprobe essentially is like probe, but you notice that it returns a request structure, and you can then use the request structure to sort of retrieve the message that you probed. And so those are kind of the improvements. It's fundamentally, you can specify the source from which to receive messages and the tags, including a tag mask bit. PSM also has a set of progression APIs like MPI does. There is a progress engine in PSM where you periodically call into PSM and you say, I want to progress my sends and receives, and these are the progression APIs. Again, extensions use the new status type that I just described, and there they are. So one thing that was kind of important to us was when we went from Intel TrueScale to Intel OMNI-PATH architecture, we wanted to make sure that existing applications that are written to the PSM API or the PSM1 API continue working on Intel OPA, right? We didn't want to sort of abandon those and say, go rewrite your applications to run on Intel OPA. And so there are two things in this space. One is what I call forward compatibility, where you take a binary application and run it as is. And the second thing I call coexistence, where imagine you're in a transition phase and you have a server with an Intel TrueScale card as well as an Intel OMNI-PATH architecture card, and you want to sort of test your application on both. And so we had to sort of think of that scenario because this is what customers have done. So as far as the forward compatibility, as I mentioned, you can take an existing Intel OMNI-PATH, you can take an existing Intel TrueScale application that is written to PSM1 or a middleware component and run it on top of Intel OPA. And we solved that problem. And so this is some of the text that sort of I described, where if you have a 64-bit tag in the original API, underneath the covers, it sort of converts it to a 96-bit tag for calling the PSM2 API. And it, as you can say, it sign extends it, or a 0 extends it to 96 bits and so on. The other key parts are a lot of the APIs that I showed had a source argument to them, like the receive. If you don't specify a source argument, which PSM1 did not have, it'll just basically treat that as null and basically say, I'm receiving messages from any source that match a certain tag. As far as coexistence, as you can imagine, we have a compat library. So it's, the PSM2 library is on the bottom. There's a thin compatibility library that sort of gives you the PSM1 compatibility, and then you sort of run your existing PSM1 application on top. And so you're now running your PSM1 application on top of Intel OPA architecture. And this is sort of the details, right? So on the send side, you're actually sending messages. What PSM does is it has two send modes. And one we call PIO, or programmed IO, which is sort of the path we expect to take when you're sending these small latency sensitive messages. And the idea here is that, it's not as heavyweight as building a Wookiee in InfiniBand. You essentially build your packet, your decent sized packet, and you essentially program it through MMIO space on the adapter. That's it. And you can use AVX instructions for this and so on. The SDMA is meant really for those sort of big bulky transfers where you allocate your buffer and you want to send it out. You program the DMA engine on the hardware. The one nice feature about this is that there's something called automatic header generation, where you can essentially tell hardware you can essentially provide hardware with a template of the header you want, and you say, I want you to change these fields on every subsequent packet. So you provide this template, you provide the buffer, and hardware says, okay, all I'm going to do is I'm going to send out the first packet, and I'm going to change this particular field you asked me to change. So it could be things like packet sequence numbers, for example. So we can send them pretty quickly using that mechanism. On the receive side, we again have two methods to receive data. One is eager and one is expected. The eager method essentially receives the data, and the data is essentially dumped in a buffer. And think of it as a bounce buffer. And then you sort of copy the buffer from there to the target destination buffer of the application. On the direct data placement path, or we call it expected, where data is directly, there's an optimization in hardware to basically place the data directly in the application target buffer. And as long as there is no errors in that packet, the application will never ever see the header. So there's header suppression happening in hardware. So between the two send modes and the two receive modes, you can sort of build this really nice way of doing MPI. If your message is small, say up to 8 kilobytes, you can use PIO send on the send side. So you're not essentially, from user mode, you're building this 8K buffer, programming the adapter with PIO. On the receive side, it's eager receive, right? Between 8 and 64 kilobytes. And these are thresholds that we chose because we thought they were sort of sweet spots. You can change these thresholds, obviously, but you can do send DMA on the send side. On the receive side, it could be an eager buffer. And then if it's above 64 kilobytes, you send DMA on one side. The reason we don't do expected receive on the receive side for sort of buffers in that middle row is because to be able to do that, we need to sort of do this negotiation. It's like if you've ever heard of sort of expected protocols, you do this sort of receive to send. Are you ready to send? I'm ready to send my buffer. Do your thing on the other side. Allocate your buffers. Let me know when it's ready to send. You receive a clear to send back, and then you send your data. So that negotiation costs something, right? So you don't want to do it for small buffers. You could, but you don't want to. And that's essentially what this is. So the point here is that PSM underneath the covers, you call PSM send underneath the covers based on these thresholds. It chooses the most optimal send and the most optimal receive to make sure your data gets there. I did mention I didn't want to get into performance, but I want to show these. These are some of the improvements. There are tons of performance improvements underneath the covers, but these are some of the differences between Intel TrueScale and Intel OPA. Better MPI latency, better MPI bandwidth, and better message rates. And the fine print there talks about the OSU benchmarks and the buffer sizes, like the latency, for example, uses an 8-byte message, and so on. It's in the slide. Quickly on PSM and OFI, I think this was mentioned in Sean's talk, but if you sort of go to the GitHub and sort of clone the OFI libfabric repository and go to the providers directory, you'll see a PSM provider and a PSM2 provider today. They're pretty stable, and there's ongoing work, but I've been told by the developer of the provider that the most of the work today is bug fixing and sort of minor tweaks here and there. So I was looking at the code last night. I encourage people to go look at it. That's the GitHub repository link. There is each of these PSM providers. Now the PSM2 provider is slightly richer than the PSM1 provider, and therefore OFI has more features if you're using the PSM2 providers on Intel OPA. And there is if you go to the OFIWIG website, there's a huge matrix that says, for all the different providers across the top, what are the different the sort of capabilities they support, and you can actually go compare PSM and PSM2. But like I said, the status is both of these providers for OFI are stable. Most of the ongoing work on this is bug fixes and so on. And finally, PSM is open source. John Fleck talked about Intel OPA's open source stuff. Ira talked about open source stuff. I think Jim later today will talk about some of the fabric management open source stuff as well. But PSM1 has been a part of OFIT for a very long time. PSM2 is in the works. We work with the distros, and we've been told that PSM2 has been accepted into RHEL 7.2 and SLES. The source code is open. It's at that link over there in GitHub, and that is the publicly, I literally Googled this last night and found that link, so it's obviously public. But the documentation is actually pretty nice. It lists in great detail the various structures, how you can program. One way to quickly learn about PSM is go download the OFI providers, and actually that's what I was doing last night, is just go look at how they've used PSM underneath the covers. And so it's pretty cool. So the takeaways that I was hoping I'd leave with is, PSM2 is the API we thought and we designed to make sure it semantically matches the requirements of MPI. That was foremost for HPC. The match queue component of PSM2 supports 96-bit tags and a receive from functionality, and that's in double quotes because basically it lets you say, I want to receive messages from this source that did not exist in PSM1. Existing applications that are written to PSM1 should continue to run on Intel OPA with that compat library I mentioned. PSM2 supports, on Intel OPA supports 2 send mechanisms and 2 receive mechanisms. There are thresholds you can set. There are environment variables and such that you can control, and you can sort of figure out your sweet spot. OFI has providers for both PSM1 and PSM2, and finally PSM is open source, so it's out there. Legal disclaimers. This one is important for this because it's pretty optimized. That's all I had. Questions?
So this is a little bit less of a question and a bit of a cautionary statement. On one of your previous slides there, close to the end, you mentioned that PSM2 is slated to go into RHEL 7.2. And I wanted to clarify that there's a different mindset sometimes between different organizations on software distribution. So PSM2 was done with the mindset that we can ship out software that's good for a single cluster, and we can possibly ship out a different thing for different clusters. Distributions like RHEL fundamentally have an unchangeable different mindset, that is, the same software must run everywhere. So the PSM2 library provides a PSM1 shim that allows PSM1 applications to run on OPA hardware. However, the second that shim is installed on the system, all QIB hardware stops working with PSM. And so if you install the PSM2 library onto a cluster that has QIB hardware and a PSM1 application stack, that cluster is now dead. And so when we included PSM2 into RHEL, we had to strip out the shim, and we can't put it back in. And that's because we have the same software that must run everywhere. And so the shim library really needed to work both with OPA and with QIB hardware in order for it to be something that we could distribute. And LibFabric is going to have the exact same problem. It has a PSM1 provider and a PSM2 provider. But if you install the PSM2 library and allow the PSM2 library to install the PSM1 shim, then your QIB support via PSM1 is dead. So that's kind of it's just one of those things that as a software distributor that sells software worldwide, we can't have a different type of software on different clusters. It's all got to work everywhere. Sure. Yeah. And so I just wanted to bring that up.
Okay. Thank you.
Thanks.
Could you clarify what developers should be using? Do you recommend using PSM directly, or do you recommend new projects to use OFI?
That's a good question. We obviously have a big push beyond, we're obviously pushing OFI big time, right? PSM, I think, will be optimal if you're using Intel OPA. But the OFI layer should be so thin that it almost doesn't matter. So that from that perspective, OFI is what I would say, because you are essentially writing your applications to something that can run on multiple fabrics, right?
Are there things in PSM that are not exposed through OFI?
I'm not aware of anything. I don't. Yeah. I'm just trying to think. I'm not aware of anything, no. Frank.
It's off. It's on? Okay. So to answer your question, the OFI provider for PSM2 exposes everything PSM2 can do, and it also exposes things it can't do. We take advantage of the features that are available to do RMA, where PSM2 doesn't naturally have a one-sided operation. So we expose a one-sided operation through the OFI provider to support RMA.
So it's actually richer to use OFI.
It's a richer feature set and a forward-looking feature set for enabling MPitch, CH4, Shemim, and so forth. and you're welcome to come talk to me afterwards.
Sure. Just another question: is there going to perhaps be a future where the PSM layer just dissolves and we just have a native?
Well, as engineers that can't resist, we've been playing with all sorts of alternatives, but I'm not going to say there's a product plan.
All
but
right.
as those that can't resist touching code, we have played with things.
All right, thank you.